These are my institutional affiliations. You can contact me at sdickson@wolfram.com or sdickson@mum.edu. I'm going to tell you a semi-autobiographical story about how I helped Danny Hillis create the equation of time cam for the clock of the long now. In 1996, I was working on the dinosaur production about across the street from where Danny was a Disney corporate fellow at Imagineering. He was designing the clock around this time, just getting started. He had seen my illustrations in the second edition of the Mathematica book. And so he said that I was the only one he could think of who could make a machine part from a mathematical equation. So the problem of keeping accurate time for 10,000 years, one idea is a solar synchronizer. The problem is the solar synchronizer sees sundial time, which needs a calendrical calculation to convert to like atomic clock time. So the analemma is the position of the sun in the sky at the same time of day for a year. And it's because the Earth axis is tilted. And it gets even worse because the equation of time morphs over the period of 26,000 years with the precession of the equinoxes. So Danny gave me a Mathematica notebook with the equation of time in it. Oh yeah, the right-hand side of this slide is an analemma sundial that has the conversion. It's the offset between local solar time and absolute time. You can interact with the equation of time cam in the Wolfram demonstrations project, and that really brings it home a lot better than just still pictures here. But here are some still frames from the equation of time demo. You can see how the equation of time morphs over, this is an expanse of 12,000 years that's cast onto the cam for the clock. So how do we turn this into a physical thing? In 1996, we used stereolithography or laminated object manufacturing. Computer-aided manufacturing applied to a mathematical equation. So this is the 1989 first advertisement for Mathematica, and it's executable code that looks like mathematics from an academic text. And here's the computer-aided manufacturing part is making a displaced surface with an edge on it that can enclose material, because mathematically thin surfaces can't be physically built. And so I came up with a data structure to do this. It associates faces with edges and edges with faces. So you can do the mesh displacement. You can get consistent normals and do the mesh displacement. I wrote a paper in 1990 that was never published, but Andrew Glassner published winged edge models in Graphics Gems 2 the next year, so it got published. Here is some Mathematica code for the iconic Calabi-Yau manifold, and the right-hand side of the slide is the traditional form of the same thing, as you would see it typeset in MathML or something like that. And so here's the Mathematica graphic of the Calabi-Yau manifold, along with a stereolithograph of the Calabi-Yau manifold. Natural mathematics compiled into a 3D surface. The equation of time mathematics you can download from the Wolfram demonstrations project, and it really doesn't look much better in the calendrical calculations book than it looks right here. And so what I did in 1996 was some fairly crude computer-aided manufacturing to turn it into an STL file. And then Danny did the casting to turn it into a machine part for the first prototype. And it's on display at the Royal Observatory in Greenwich, England. So it's an iconic object in its own right now. And here's just another plug for my employer. Stephen Wolfram is doing fundamental physics again, and I think it's really cool. And it's an open project. Anybody can join and contribute to the to finding the fundamental theorem of physics in computation. And thanks to the Long Now Foundation and Brady for allowing me to be here.